Welcome back, quantitative analysis students. This is Mr. Marquetta, and today we're going to talk about implicit differentiation. We're also going to discuss all the things you need to know for exam number 2, which is scheduled for this Wednesday at 4:30. I've collected here all the important examples out of 11.3, and also the primary concept of what implicit differentiation is. I anticipate this will take maybe 45 minutes to go through, and then we are going to dismiss for the day. It'll be a little bit of a shorter day than usual because I'm expecting that you'll use this time to make sure that you focus closely on the exam review and get ready for Wednesday's exam. Let's get started. We're talking about chapter 11.3, implicit differentiation. Today is July 26, 2021. First, what do we mean by implicit? I want you to think about the word implicit and compare it to the word explicit. You probably heard warning content, explicit lyrics, things like that. Explicit means exactly what it looks like. There's nothing to be figured out. There's no it's very clear and direct. Here it is. Implicit is that you have to look a little bit below the surface. It's a little bit deeper. The word implicit means it's there, but you have to search a little bit more for it. So when we say explicit in mathematics, what we're trying to say is, I'm telling you what x is. X equals 5. That's explicit. If I told you I'm telling you what x is, 5x squared plus 2x plus 9 equals 3, you got to think a little bit before you can figure out what x is. In other words, x is implicitly given there. And when we talk about differentiation, up until now, we've always done only explicit differentiation, meaning we've always gone straightforward with the function we see, and we've differentiated it straightforward. Instead, what's going to happen now, instead of it being y equals a function like usual, you're going to have an equation that has y and x on either or both sides. And in other words, you're not going to just have to think about x when you're doing derivatives. Now you have to think about y as well. And you're going to, instead of just solving it for y and then taking the derivative, or only taking derivatives when it starts with y equals, you'll have equations that include both variables on either side. And implicit differentiation is a way for you to work through an equation so that you can find the derivative of the variable with respect to x. But in the same way, you don't have to solve the equation first. So there are a couple of different ways to look at implicit differentiation, and there are a lot of great applications here. We're going to do them today. Let's start by talking about the actual methodology behind performing implicit differentiation. The first thing you do when you're trying to perform implicit differentiation is just look at the equation you have and differentiate both sides with respect to x. What does that mean? That means the same thing it always meant, the same kind of derivatives that you've always seen before. But if you see a y, you have to consider it as if it was a constant, like a 4 or a 13. In other words, y is not a variable that's important in this case. Instead, x is the important variable. So if you see 5x, you know the derivative is 5. If you see yx, you should think the derivative is y. In other words, because y is something of a constant in this case. The other thing we have to think about is when you do take the derivative of something, we do have to also consider the chain rule, and the chain rule does become a regular part of it because the derivative of y itself is actually dy dx. So that is going to come up again, and you'll see that in a moment too. But for the most part, what I want you to remember about this methodology is it starts with differentiating both sides with respect to x, and that's kind of big now. Those words with respect to x usually fell to the wayside before when we were talking. It means something a little bit more important right now. Also, we then the next second thing we do is we collect all the dy dx terms. In other words, every time dy dx appeared in our next line of math, because we're doing differentiating this way, is we take all the dy dx terms and bring them all to the left side, and then put all of them to the right side.
Where am I going to put it? Where are we putting it?
Okay, guys, I'm going to ask you to please try to remain mute if you can, and if you're not, that's okay. I'll go in and mute you, but somebody creeped in by accident. Hello. All right, and anyway, where were we? We're talking about part 2. Part 2 says what you do after you do implicit differentiation is you take all of the dy terms and dy dx terms and group them together and bring them all to the left. And you leave all of the other stuff that doesn't have dy dx in it on the right so that you can divide everything out and solve for dy dx. That's what they mean by factor out and solve. Now, saying it here right now, it's a little bit hard to grasp because you're not looking at an example. I'm going to go through 3 or 4 examples with you. And then after we go through those examples, I'd like to come back to this slide again and review how we have followed each of these 4 different important rules here, or steps rather, to get our answers. All right, so let's take a look first now at example 1. In example 1, part A is asking you to use implicit differentiation to find dy dx for y squared equals x. Okay, at this point, what I'm going to do is I'm going to ask you guys to please go ahead and change your view in the top right to speaker view. That way you'll get a nice clear image of what I'm writing here. It'll fill up the screen instead of being a very small rectangle, and you kind of have to be able to follow the algebra here. So you want to toggle over there. You want to toggle over into speaker view up there in the top right. Excuse me. So now what we're going to do is we're going to take the derivative of both sides with respect to x. All right. Let's start by taking the derivative of the left side. What is the derivative of y squared? Well, y is not x, but we're going to still, in some cases we would treat it as a constant. I was talking about that earlier, but in this particular case, we're going to do implicit differentiation. Start by saying, how would you take the derivative of y squared? It would be 2y, right? But the problem is, it's with respect to x. So if it's with respect to x, then we have to say, what's the derivative of what's inside? Meaning for y squared, I had something of a chain rule where I had something squared, meaning whatever I do, I have to make sure I multiply by the derivative of what's inside there. So whenever you take the derivative of y like this, you include times dy dx. Now, I want to warn you right now, the handwriting starts to get ugly here because you keep multiplying by this fraction dy dx and it never looks nice and neat. It's always awkward and the fraction is floating. Usually y is hanging down. It's a mess, okay? But if you just try to keep really neat handwriting, you'll be in good shape. The other thing you'll do now is to take the differentiation of the right side. What is the derivative of x? The answer is 1. And by the way, since we took the derivative of x, we don't have to think about the chain rule and implicit differentiation because it's x. We're doing it with respect to x, so we don't have to include that. Now, the next step is you're asked to find dy dx. So this is a great statement, but it's implicit. What we have to do now is solve it for dy dx. And the way that we do that is by dividing out the 2y. Now, at this point, you're looking at some very large writing here, and it turns out being very uncomfortable math, as you can see. But this is our basic concept, is what we mean by trying to follow those 4 rules. You start by doing implicit differentiation across, meaning plain old differentiation like you already knew it, but whenever you have y in there, make sure that you multiply by the derivative of y with respect to x, because it's not with respect to y, it's with respect to x. And the chain rule implies that you could take the derivative of something squared, but when you're done, make sure you take the derivative of what's inside. The derivative of what's inside is the derivative of y, that's dy dx. Then on the right, what's the derivative of x? The answer is just 1. And now you can divide out 2y to both sides, and you get your answer like you see here. Notice this time the derivative dy dx is actually in terms of y, not x. Sometimes you'll have just y, sometimes you'll have x, sometimes you'll have both y and x. In that respect, when you're asked about certain things having to do with points, make sure that you use both of the points. Right? For example, example 1b now is going to ask you to use this very formula to find a specific slope. For part B, it's saying find the slope of the tangents to this graph, which you just found the derivative of implicitly. Find the slope of the tangents at the points 4, 2, and 4, -2. Let me jot those down, and then we'll show you how to do that. Okay, recall that it is going to have a derivative of dy dx equals 1 over 2y. Also, the points that we're asking about are 4, 2, and 4, -2. So for the point 4, 2, I have x is 4 and y is 2. So this function becomes 1 over 2 times 2, which is 1/4. Here, we have an x of 4, and we have a y of -2. So the formula calls for 1 over 2 times y, which is -2, giving a solution of -1/4. Notice in both of these cases, x was not necessary because the formula itself did not have x in it. But if x was in the formula, of course, you would put 4 in all those places and finish the calculation to answer the solution. Remember the story of the slope of the tangent line. The derivative is the slope of the tangent line in code. The code is, do you know what y is to get it this time? Here's another great example. Find the slope of the tangent to the graph. And then we have an equation, and then we have a certain specific point. Let's first jot down the equation. And you're doing it at root 5 comma 2. Okay, so if you're going to try to figure out now the derivative here, you'll take the derivative of both sides. In this case, on the left, we have something of a sum, or we could use the addition or difference rule, the sum or the sum rule there, and we could do each of these things individually, starting with x squared. What is the derivative of x squared? That we learned a long time ago. It's 2x, right? What is the derivative of a y squared? We actually did just demonstrate what it is. Let's look at that one more time. We demonstrated that it does turn out to look just like this, right? This is the derivative of y squared. We discussed because you do the thing, you do the exponential rule, make it 2y, and then multiply by the derivative of what's the side, which is dy dx. So the derivative of y squared then will be 2y, just like this is 2x, but it's also times dy dx. And now the derivative of 9 is 0, right? There is nothing, and now equals. Now the derivative of 0, what's the derivative of 0? The answer is 0. Why? Because 0 is a constant, and the derivative of all constants is 0. Next, I'm trying to solve for dy dx. So let's keep this term right here. This is one big long term. Let's keep that term there, and let's subtract 2x out. And now I have on the right, I'm sorry, on the left, 2y dy dx equals negative 2x. Now I'll divide both sides by 2y. And these 2's knock out, right? And now I have dy dx equals negative x over y. So let's review. What did we do? We did all 4 of the important rules that we were talking about. We took the implicit derivative all the way across of every single term we saw. Then we collected the dy dx terms to the left and everything else to the right by doing this. And then we eliminated we didn't have to factor this time because it was just this, but later on we'll have to factor, and I'll show you what that looks like. But we isolated dy dx by dividing out 2y, and we wound up simplifying over here a little bit to get this expression negative x over y. Now, if you want to know what is the what is the slope of the line that is tangent here at this particular point, you have to use this x value and this y value in the derivative to answer that question. So it's not really very many calculations at all. You just kind of throw it together. Equals negative root 5 over 2, following this formula right here. Looks like I got to get rid of this marker. So this is the solution they want, and it's based on plugging x and y from the point they gave you into the derivative dy dx, which is found implicitly through here and includes both the variables x and y. Notice the questions are all the same question. It's the same format again. It's the wording, find the derivative of find the slope of the tangent, find the slope of the tangent, it's the same thing they say over and over again. And what it means is take the derivative, then plug in the point. That's what it means, okay? Now for part 3, we're not just asking you to find the slope of the tangent, we're finding you to find the equation of the tangent line. Now that's a little bit different. How do you find the equation of the tangent line? Well, first, how do you find the equation of any line? You need a point and a slope, right? Well, I have a point, point's right there, 2, negative 6. The slope will be the figure I get after I find the derivative with implicit differentiation, and then plug that point in, get an answer. Like I did before, I had negative root 5 over 2. I'll plug 2, negative 6 into my derivative and get something, and that'll be the slope. I'll use that slope and this point and the point slope formula to get the answer of what the equation of the tangent line is. We talked a little bit about that earlier, how to write equations of lines and things like that. Just be on top of the different formats. You know, you have point slope, slope intercept, and general form. Sometimes they ask you for one or the other. And when you do your web assigned practice, you'll see cases of all of them. And it's important you're able to kind of maneuver back and forth between them. Okay, so let's start by writing down this equation here, and we'll focus on trying to find the equation to the tangent. The equation is x cubed plus xy plus 4 equals 0. And we're doing it at the point 2, negative 6. All right, so we're going to do this with implicit differentiation, and what that means is we're going to go across one thing at a time here, and again, we see a sum rule happening because we have 3 terms in a row here, and we're going to do the derivative of each of those terms. Then when we're done with that, we're going to plug this point in and figure out what the derivative would be at that point, the slope at that point. All right, now, let's look at x cubed. The derivative of x cubed is 3x squared. That's old news, right? Now, the derivative of xy, let's take a minute and figure out the derivative of xy. I'm going to do it over here, all right, using the product rule. If you remember, the product rule looks like this. uv quantity prime will be u prime v plus v prime u, okay? Now, in this situation, if x is going to be, and I'll put a little note here, this is u, and this will be v. So let me just kind of jot that down. U equals x. V equals y. So that means what is u prime? U prime is going to be 1. The derivative of x is 1. What is v prime going to be? V prime is the derivative of y. Here's a trick question for you. What's the derivative of y? The answer is dy dx. Okay. Now, let's assemble the derivative using the product rule template here, right? And I'm going to get for this u prime v plus v prime u. Simplify it a little bit, it's y plus x dy dx. Okay, so this right here is the answer to what is the derivative of xy. So I'll put that in now. Okay, next. And if you need to see that again, here it is for a minute. We went through the product rule and we did a case and we wound up with this is our final expression for the derivative of xy. So I put that in right here now as the derivative of this part. Okay, great. Now, what is the derivative of 4? The answer is nothing. What is the derivative of 0? Again, the answer is nothing. So this is what it looks like. Now, like before, what I'm going to do is I'm going to solve for dy dx. I'm going to bring all of the terms that are not dy dx terms to the right. I'm going to keep the dy dx terms that I have on the left. If there were any over here, I'd bring them over to the left. So how many terms do we have here? We have 1, 2, 3. Even though this may look like 2 terms, there's a multiplier here. This is all one big term. So we cannot subtract x. We can only subtract these things. You could do them all at once if you want. And then you get this. And now to finish up, you would divide x out. And now, as you can see, here is your expression for the derivative of y with respect to x implicitly. As you can see, it does involve x and y. Specifically for the case of x equals 2 and y equals -6, let's put those values in and see what we get. All right, this is going to be -12 plus 6 is -6, and it's going to be -2. So a little arithmetic here, and I know that you could follow the arithmetic. I'm not going to drone on about it, but get a calculator if it helps. But when you substitute, you're supposed to get -2. So now what does that mean? That means that we have a new question to answer now. What is the equation of the line that has a slope of -2 and passes through the point 2, -6? Well, that's not hard to do. When to try to figure that out, what we would do is we would just go ahead and write the point slope formula out. Point slope form, if you recall, goes like this. Y minus y1 equals m times x minus x1. There are other ways to do this. Some students like to use y equals mx plus b, plug the number in, and then figure out what b is and all that. If you want to do it that way, you can do it that way too. In other words, there's more than one way to do it, but the most direct way to figure out the equation of a line when you have a point and a slope is use the point slope formula. This case would make this x1 and this y1. All right, and so that would make it that I have y minus, now y1 is going to be -6, Notice when I do minus negative, I use parentheses. It looks a little neater and it's much more clearer and easy to understand. Later on, I'll turn that into a plus, you know. The m is going to be, as we have found earlier, -2. So I'll use -2 there. And then x minus x1 has a quantity of 2. Let's simplify a little bit. How about y equals -2x minus 2? All right. Now, this is a great example because when you look at this function, I'll try to put it this way. When you look at this function here, this is a pretty ugly looking function when you graph it. And it's hard to believe that there is a point on there that has a perfect equation like this. Let me show you that you can see what that looks like on graph paper. Okay, friends, what we're doing right now is we're going into Desmos and we're going to try to graph these functions and take a look at what it turns out looking like here. I think that'll help a little bit so that you have a good idea of what's going on with the functions. So first, let's graph the function that we were doing, x cubed plus y plus x plus xy plus 4 equals 0. What am I doing here? Plus 4 equals 0. There it is. Okay. What a funny looking, look at how this one came out. Strange, isn't it? Look at that weird function. All right. Next, let's figure out where is this point, 2, -6. Well, when we graph the equation of the line we just found, it'll be a tangent to it. Y equals -2x minus 2. All right. Now look very, very closely right there. Okay. Hmm? Okay, so the equation of the line is a curve. And on the curve, there is a point somewhere that it passes by the point right at that place. And it only barely touches the curve there. That point is 2, -6. This function, x cubed plus xy plus 4 equals 0, is the red line. And then the other line touches it barely in one place. That's at 2, -6. That's what we mean by the equation of the tangent line. Let's look at example 4 now. Example 4 says find dy dx, and we have an equation. Let's write out the equation, and then I'll focus with you on how to get the answers. Okay, now again, this is the kind of thing that you just have to be very careful and deliberate and go step by step with each thing. I'm going to go through it and I'm going to ask you to please follow closely along. Again, I want you to let me know if you're getting lost or if you're not able to understand it. Just let me know and we'll go over it a little bit more. So for this, on the left, we'll do each term one at a time. Again, we have a sum on the left and we have a sum of 3 things on the right. On the left, the x to the 4th, the derivative of x to the 4th is 4x cubed. Then we have 5xy to the fourth. Looking at 5xy to the fourth, we got to start by thinking about how we have a product here. You could use the constant, rather the coefficient rule and write the 5 and forget it for a minute, and then go in with the derivative of what that is. Let's stop and figure out xy to the fourth, what the derivative of that would be. In the case of xy to the fourth, this will be u, and this will be v. So u prime will be 1. Well, let's write it this way. U equals x, right? So the derivative of u is 1 then. V is y to the fourth. So the derivative of v prime, is going to be 4y cubed. But then don't forget to multiply by the derivative of what's inside, which in this scenario is y, and then we're going to use dy dx there. Now, we're going to use the product rule here. And we're going to put these together now. U prime is 1. V is going to be y to the fourth. V prime is 4y cubed times dy dx. And u is x. And that's times x there, right? So this is u prime v right here. And this is v prime u. And that's a multiplier. So to make it just a little bit nicer, I can rewrite it now to be y to the fourth plus 4xy cubed times dy dx. This is where your algebra skills come into play a little bit if you're in a position to be able to know how to simplify things or put them in a nicer order so it's easier to write or repeat or to transfer over. So this is the answer of what the derivative of this quantity is. Let's take this entire expression and put it in next. Y to the fourth plus 4xy cubed times dy dx. And then close the parentheses. Okay. Now, as you can see, we're starting to run out of room a little bit. That's okay. When I run out of room with equations, what I do is I indent. So equals, here's the other side of the equation now. The other side of the equation is going to be the derivative of 2y squared, which we know should be 4y. And then the derivative of what's inside y is dy dx. Next comes the derivative of x, which is 1. And then the derivative of -1, which is 0. So now let's see if we can simplify a little bit. I'm going to distribute this. Maybe I'll get lucky and I'll be able to put it all on one line. Let's see. Starting with 4x cubed plus 5y to the fourth plus, now I'm thinking about 5 times 4 making it 20, xy cubed times dy dx equals, on the right, 4y times dy dx plus 1. Okay. I was able to fit it all in one line. Great. Now, this is the part that we were talking about earlier. And I'd like to focus with you now on making all of the dy dx terms come to the left, and in the same way, making all of the other terms that are not dy dx terms go to the right. So what I'll do is I'll leave the 1 where it is. And I'll leave this entire term where it is because it has dy dx in it. I'm going to bring this one over. And then I'm going to bring these over too, -4x cubed, and also -5y to the fourth. As you can see, it's kind of a mess. It's a lot of math. So what you have to do is try to make it real clear by putting them all together. These will knock out. These will knock out. These will knock out. And now let's see if we can clean it up a little bit. We'll take it from here. Okay, on the left, I have -4y times dy dx. That's this term. And then I also have this term, 20xy cubed times dy dx. That's my left side. Now on my right side, I have all of these three things. -4x cubed, -5y to the fourth, plus 1. I'm going to pause there and have a look at that. What I did was I brought all of the things that were dy dx terms to the left. That's why -4y is here and 20xy cubed is there like that. That's my left side. Now on the right side, I bring all of the other things that you see here to the right. And also 1 is already over there on the right. So I'm going to put them all together, all 3 of them, and it looks like this. This was step 3 in the implicit differentiation setup, where you're supposed to bring everything to the group together, the dy dx terms. Now you're going to use factoring and factor out dy dx, because as you can see on the left side, it is in both of these terms. It's in this term and this term also. So let's pull dy dx out of both of those terms with our old factoring technique. It's called greatest common factor. We'll pull out dy dx, and we'll set up a new brackets to be negative 4y plus 20xy cubed. Now, see how the GCF factoring method brings you back to the distributive property, meaning if I took this and distributed it through, I'd wind up with this term, and then when I got to the 20xy cubed, I'd wind up with this whole term. So I have factored out dy dx, and now on the right, I still have that polynomial there, negative 4x cubed minus 5y fourth plus 1. To finish up now and get my final derivative, I can isolate dy dx by dividing by the entire expression in the brackets. And then I have my solution. As you can see, the solution is always going to be complicated looking like this. You have very high exponents. You have y to the fourth. You have xy cubed. It's not really very pleasant. You're not going to get 1/2. You're not going to get 15. When you're done with your answers, you're going to see pretty complicated expressions. And that's why when you're going through, you have to really be very careful and pay close attention to every detail, because it's so easy to make a small mistake, or to accidentally forget the negative sign, or maybe write x instead of y. I've seen students do things like that. So this is a great example also, by the way, of how to use those steps of implicit differentiation. And now before we go on, I'd like to share with you again those steps and kind of reiterate how we did apply them here to get the answer to this solution. Let's go back. First, we did the differentiating of both sides like we have here. We did the derivative of both sides. Then we collected all the terms to the left, which was what all of this work was here when we collected to the left. Then look at how for part 3, we factored out dy dx. We factored it with a big bracket. I like to use a bracket because I know that's the factoring part of it. And then last, we solved by dividing out that bracket. So we have a simplified answer of dy dx there. Okay. Now, as if that isn't fun, let's try to throw in logarithms. Let's do it with logs now. Okay, so in the next example, we're going to find dy dx, but we have a natural log. We'll try to recall how to take the derivative of the natural log and use that as part of our approach here. So we're doing example 7a, natural log of xy equals 6. All you're trying to do is find dy dx. So there are a couple ways that you could do this. In a case like this, you could start by going in with using the argument of xy and then finding implicit differentiation, or it's a little bit easier if you go in by simplifying the logarithm first. The natural log of xy, there is something called the product rule in logs that says if you have an argument that is a product like x times y, you can rewrite this to be the natural log of x plus the natural log of y. So that be the case, it kind of relieves the problem of doing the product rule, which is lengthy. And, if you can find ways to make it simpler before you start taking the derivative, you have a little bit of an advantage. Like, for example, here, it's an easy log trick if you have a product in there to split it this way first. Anyway, all we've done here is apply a log rule. We didn't do any calculus yet. We didn't do any differentiating yet. All we did was we applied the log rule and we split it. So now let's do the calculus and apply the derivative. What is the derivative of the natural log of x? We learned that it was 1 over x because of limits. And now what is the derivative of the natural log of y? Well, like we had before, well, it must be the natural log of y must be 1 over y. But remember that y is not the variable we take it with respect to. Instead, we have to show that we mean to multiply by the derivative of what's inside because of the chain rule. So it will be dy dx like that. And now last but not least on the right, the derivative of 6 is 0. All right, so this one is really kind of not as hard because I applied the natural log rule that we know of. Again, we're going to try to solve for dy dx. So let's group all the dy dx terms on the left and everything else on the right. Notice there were only 2 terms here, this one and this one. So I'm going to remove this one now, like so. And that'll bring me to 1 over y times dy dx equals negative 1 over x. And now, to simplify, I can either divide both sides by 1 over y, or if you're sharp with algebra, you might realize you can multiply both sides by y, and it'll do the same thing. It does make it a little bit easier to think of. And so our final solution then is negative y over x, like you see here. That was an example with logarithms. What I'd like you to remember most from doing derivatives with logarithms is try to apply old log rules before you start doing hard derivatives using product rule and quotient rule. You can take any log and simplify it. For example, if you had the natural log of x over y, you would have to do the quotient rule to that if you were doing it as a straightforward derivative. But since we have log rules, you can write that to be the natural log of x minus the natural log of y, and that's much easier to find the derivative of than to define the derivative of this straightforward. So just keep that in mind. Try to apply rules if you can. And when you do them with exponents, try to do it the same way. In fact, here we're going to do an example now involving Euler's number e. This one is 4x squared, and this is example 7b. This is 4x squared plus e to the power xy equals 6y. So in this case, when it comes to this exponent, this is the kind of exponent that it's not very easy to use a quick rule the way we did with the natural log and get a shortcut. There's no real shortcut to this, but even so, the derivative of Euler's number is very easy. If you remember, it turns out being the same thing as it already is. When we get to that, it's just a matter of remembering to multiply by the derivative of what's inside because of the chain rule. So let's go on each one. The first one is 4x squared. Derivative will be 8x. And now, again, here we are with Euler's number, e to the xy. The derivative of e to the xy is e to the xy, and that's the easiest derivative there is. So now we say, what's the derivative of what's inside? The derivative of xy. We did figure that out already, didn't we? In fact, that was one of the first things we did. Let's take a look through our notes and see if we could find that. Remember when we studied this example? This is the case of what is the derivative of xy? The derivative of xy, as you can see here, based on these ideas, turns out being this expression. You can always use this again, because if you figure it out again and again, you'll waste your time. The derivative of xy, we figured that already, and it's this. So let's write this next in our math. It'll say y plus x times dy dx. That is the derivative of what's inside. And last but not least, equals 6 times, what is the derivative of y? It is dy dx. All right. So now that you've got that, you can now go through steps 3 and 4 of the process where you start isolating the variable dy dx. The only thing here is, remember, we have a distributive property, and it's going to get to be a little bit ugly with the handwriting. You're going to distribute it to this first term, and then you're going to distribute this to the last term, as you could see here. Now you got to try to use some fun handwriting, and you write some really extreme calculus here. Here we go, guys. Okay, it's going to look like this. First, I'm going to write 8x plus ye to the xy, meaning when you write, the correct penmanship is to write so that that little exponent is the last thing you wrote. It looks a little bit nicer floating up there that way. Then multiplying this times this term, I'm going to squeeze that e term right in between and make it look like this. Xe times dy dx. Put that little xy up there. And then last equals 6 dy dx. Now we're in a position where we have to bring things over. We're going to bring this one over and this one over, right? And we're also going to bring this one back, okay? So this is going to change sign and be negative, and so are these, because I'm moving them. So on the left, the only thing that has not moved is this. This is going to stay. It'll be xe to the xy times dy dx minus 6 times dy dx equals minus 8x minus ye to the xy. Okay, it seems like gibberish, doesn't it? This is why people go crazy for calculus. This is a little bit upside down, all this stuff. But we're on the right track, and we are almost done. How many terms do we have? Although it's a little bit unclear, we do have 2 terms. Here they are, right? So let's factor out dy dx now. And it'll be xe to the xy minus 6 in there equals this expression, negative 8x minus y e to the xy. So to isolate, I would divide by that bracket, putting that expression underneath here. And this is what we want for our solution. All right. I'll put quotes in there so that you understand it, All right, now I hope that that's clear. That's the way you're supposed to do differentiation implicitly. You have some great examples there. These are straightforward calculus cases. What I'd like to do with you now before we dismiss is try to focus on a couple of applications. And these applications, remember what our lesson is. It's about implicit differentiation. So all of the stuff that you're going to see there is going to be basically the same process again. Here's an equation. Take the derivative with respect to one particular specific certain variable, then use a point, plug it in, and get an answer, right? For example 5, we're talking about production. It says, suppose that a company's weekly production output is 384,000 and that this output is related to hours of labor X and dollars of capital investment Y. And then we have a formula. Let me jot down the formula. Find and interpret the rate of change of capital investment with respect to labor hours when the labor hours are 512 and capital investment is 64,000. So just make sure that you know what's going on. X is hours of labor. Dollars of capital investment is Y, so Y is 64,000, not 64. Things like that you just kind of have to keep in the back of your mind while you're doing it. All right, let me jot down the question, 384,000. And this time I have some fractional exponents. And when we're done, we're going to use the point 512, 64,000. Let me put that down here. Okay. Okay, so again, it's the same procedure. On the left, the derivative of any constant is 0, as we have described. Now there's a 30, that's our coefficient rule, we'll leave it there. And now I can look at this as if it's a product. Let's figure out what that would be using the product rule. Recall that the product rule looks like this. In this case, we're trying to find the derivative of x to the 1/3, y to the 2/3. We're trying to find the derivative. So u is x to the 1/3, and v is y to the 2/3. So to find the derivative u prime, I will use 1/3 as my new coefficient, and then subtract 1/3 minus 1. Just try to remember 1/3 minus 1 is going to be negative 2/3. Right? Okay, that's a pretty nasty exponent. Make sure it's clear, you don't have to write it really tiny. It's okay if your font size isn't really, really small. You can show it's an exponent, just draw it a little bit higher and make sure that negative sign is very clear because it's a small font, Same thing will happen here with v. V prime, the derivative of this will be 2/3 y, and now instead of 2/3, I have to think about 2/3 minus 1, which you should know is negative 1/3. All right, so now I have expressions for u and v, and u prime and v prime. Let me see now if I could use those ideas to take this derivative. So it should be, in parentheses, u v prime plus v u prime As you can see, it's very discouraging. It's easy to screw it up, but you got to kind of stick with it. All right. Now, what's missing here? What's missing here? Right here, when you took this derivative, you had to include times dy dx. And that, my friends, is where the entire thing lies, is right there, that dy dx. So that dy dx actually does belong right here. Now, one way you could do this to make it easier on yourself, especially considering there are all these nasty negative exponents and things, is don't solve it for dy dx. Instead, go straight in with this particular point right here and see what you get. In other words, write 0 equals 30 times, and now x is 512, and then times 2/3, and y is 64,000. Okay, plus y to the 2/3, which is 64,000 to the 2/3, times dy dx, times 1/3 x, which is 512, to the 2/3. All right, and then of course close the bracket if you can. Now, the good news is it's easy to find the 1/3 power of these things. Let's talk about a little times table fact, a power fact. Happens to be true that 512 to the 1/3, that's the same as the cube root of 512, which everybody knows what that is, right? It's 8, isn't it? Yeah, it is. Cube root of 512 is 8. Likewise, what is the cube root of 64 grand? The answer is 40. Now, that be the case, 512 to the 2/3 is going to be 64, and 64,000 to the 2/3 is going to be 160. Now you could do this with a calculator, but these are times table facts and they turn out to be nice whole numbers, which gives you a little bit of an indication that you're probably going in the right direction. Just remember, if it's to the negative 1/3, then it's going to be 1 over it. That's the only difference. All right, so that be the case, we're looking at an equation that says 0 equals 30 times this number is going to be 1/8 times 2/3 times, and this is going to be 1 over 40, plus, then this is going to be 160 times dy dx times 1/3 times 160. All right. Now a little computation with the calculator. We can multiply, or we could try to simplify here. Wait, 500, so this is actually the number 8 on top. So that'll go like that, leaving a 20. And then this will go 5 and 2. So what you have is 2 over 15 there. And then this is going to be 160 times 160, and that's negative 2/3. Yep, it is. So these actually cancel out with 1/3 at dy dx. Taking that answer, we would have 0 equals 30 times 2 over 15 plus 1/3 times dy dx. Using the distributive property, you can distribute 30 through, and you'll wind up with 0 equals 4 plus 10 dy dx. And if you solve, pull out that 10, I'm getting negative 2/5 as dy dx. And that is the answer specifically at the case where x equals 512 units at a cost of 64,000. There is one more example here. I'd like to show you how to do this one last example, and then after that, we'll talk about our exam, and then we'll dismiss for the day. The question is an application. It says, suppose the demand for precision ink headphones is given by this formula, where P is the price of per set in dollars, and X is in hundreds of headphone sets demanded. Find the rate of change of demand with respect to price when 1,900 sets are demanded. Now remember, it says with respect to price. What that means is that this kind of looks like X equals, not Y equals. it's actually the P that's really very important here. It's with respect to price. So let's write it down and let's consider X as if it was the Y. And we're not going to be figuring out dy, dx. We're going to be finding out dx, dp. All right. So the formula is P equals 10,000 all over X plus 1 quantity squared. We're trying to find dx, dp. So in order to do that, okay, there we go. In order to do that, the derivative of P then is going to be 1. And then this, I'm going to, well, before I do that, I'm going to rewrite this to be P equals 10,000 times X plus 1 to the negative 2. I'll make that a little tiny bit easier on myself. And now I'm going to try to figure out the derivative of P of X with respect to P. So that means this is going to be 1. And this is going to be, of course, this is a coefficient. And now I have to take the derivative of this. Well, that's going to be take this exponent and make it negative 2, rewrite it, and bring it down 1, negative 3. But don't forget to multiply by the derivative of what's inside. Okay, so now that negative 3, we can write that to look like this. 1 equals, this is 20,000, right? Negative 20,000 all over X plus 1 quantity cubed times dx dp. If I multiply both sides by the reciprocal of that, I'll have on the right isolated dx dp, and then on the left, I'll have this reversed, or the reciprocal of it, which is x minus 1 cubed all over negative 20,000. This is the solution we were expecting for you to get to that question. The last part of the question is asking you to figure out what happens when 1900 sets are demanded. And remember that the X is the number of sets. So if we're asking for 1900, and remember that X is given in terms of hundreds, then what we're going to do is we're just going to plug 19 right in there, which gives us 19 minus 1 quantity cubed all over negative 20,000. And you can figure that out with your calculator. It's going to be a very big, ridiculous number, and that'll represent the demand in terms of P when you are selling 19,000 headphones. All right, before we dismiss, there is one last thing I want to share with you. Let's share this. And I hope that was informative and helpful. We're going to go now with talking about our exam. Your exam will be available from 4:30 until 6:45 on Wednesday. So that means there will not be a Zoom that day. And we're going to give you 2 hours and 15 minutes as usual to complete exam 2. They will be varied from student to student, and also you'll be varied with order and values. So you may see different numbers than your classmates. You might see a different order than your classmates. You will only see one question at a time. And it is important you answer that question carefully because you won't be able to answer it again. And you also won't be told immediately if you're correct or not. The other thing you should know about it is your last final score is always an estimate. In other words, if you look through your exam and you find that there was a mistake in the way that something was entered or the way that it was interpreted through WebAssign, or sometimes you accidentally don't put a capital X and it's supposed to be a capital X and they mark it wrong, or things like that, all you have to do is don't panic. Just let me know in an email. I'll totally go and fix it. It only takes a minute and it happens all the time. It's a natural part of online learning. If you see something like that in your answers, please let me know. But please be advised, my friends, you will not see your answers until after the day has gone by, and in the next morning the answers will be available. All right. Also, please make sure you do exam number 2 review beforehand. It's really important that you go through that because all of those things are all right there for you to study. All right. So I hope that was informative. I'm going to stop our recording and then I'll open up the floor for any questions.